Guys, I am Mamta from BSc Chemistry Honors final year. Today I am here to read about organic chemistry topic organometallic compounds. So we start from introduction part. Organic compounds in which metal atom is linked directly to a carbon atom are called organometallic compounds. A large number of metals, example lithium, sodium, magnesium, zinc, mercury, lead, cadmium, etc. From such compound, the organic part is generally an alkyl or aryl group. They are named simple by adding the name of the metal to the name of the organic group is linked to the metal. For example, methyl lithium, ethyl magnesium, and butyl lithium, diethyl mercury, tetrahalide lead, phenyl lithium, dimethyl cadmium, diethyl zinc. The carbon metal bond in the organometallic compounds differ widely, varying from bonds which are essentially ionic to those which are largely covalent. For example, this. Thus, the extent of the ionic or polar character of the bond is largely determined by the electropositive nature of metal. More electropositive the metal, more is the ionic character of the carbon metal bond. In general, the ionic character of the carbon metal bond follows the sequence. The reactivity of organometallic compounds also depends upon the nature of carbon metal bond. Generally, the larger the ionic character of the carbon metal bond, more reactive is the organometallic compounds. However, compounds having intermediate ionic character are of greater importance because of their lower reactivity and selective nature of their reactions. Organometallic compounds are extremely useful for synthesis of vast variety of organic compounds. Apart from these, many of the organometallic compounds are commercially important as well as, for example, tetrahalide is extensively employed as an anti-knock compound. Organotin compounds are used as antioxidants in rubber products. Phenyl mercuric acetate is used a fungicide and disinfectant, and the organoerancic compounds are used in medicines. Organomagnesium compounds, Grignard reagents. Organomagnesium halide are extremely important reagents in synthetic organic chemistry. These reagents are commonly known as Grignard reagents after the name of discoverer Victor Grignard, who recovered the Nobel Prize in the chemistry in 1912 for this discovery. The general formula of Grignard reagents is RMGX or ARMGX, where R represents an alkyl group and AR represents an aryl group. Preparations. Grignard reagents are prepared in the laboratory by the action of alkyl N or an aryl halide or on magnesium metal in dry ether. Beside the ether, tetrafuran, dioxane, dimethylhexane, or dimethyl ether of diethyl glycol, tertiary amines, etc., can also be used as a solvent. In fact, tetrahydrofuran is considered to be a best solvent since it increases the reactivity of an alkyl or aryl halide towards magnesium. It is because of its reason that the Grignard reagents of less reactive aryl and vinyl halide are prepared in tetrahydrofuran. When bromobenzene is react with magnesium in the presence of dry ether, then phenyl magnesium bromide is performed. When chlorobenzene is react with magnesium in the presence of tetrahydrofuran, phenyl magnesium chloride is present. Vinyl chloride is react with magnesium in the presence of tetrahydrofuran and heating. Vinyl magnesium chloride is present as a product. Further, it has been found that of the given alkyl group, in the case of formation of Grignard reagent, is the order of iodide is less than bromide less than chloride. The alkyl or aryl magnesium fluorides are, however, unknown. For a given halogen atoms, the order of reactivity is this, etc. The formation of Grignard reagents becomes increasingly difficult with increasing in the number of carbon atoms in alkyl group. The use of tertiary alkyl iodide is avoided since they readily lose a molecule of hydrogen iodide to form an alkene. Tertiary alkyl chlorides may then be used. Procedure for the preparation of Grignard reagents. Alkyl or aryl halide is added slowly to a perfectly clean and dry flask containing dry magnesium turning covered by the layer of absolutely dry ether or tetrahydrofuran. The reaction mixture is warmed a little when an exothermic reaction would soon start if reactions does not start within 5 minutes. A few crystals of iodine are added and the reaction mixture is warmed a little. A vigorous reaction soon set in and magnesium gradually dissolved, forming a cloudy solution of Grignard reagents. Precautions in the preparation of Grignard reagents. During the preparation of Grignard reagents, the following precautions must be observed. The apparatus should be perfectly dry and protected from the moisture by using a CaCl2 guard tube. All the reagents and solvents, that is alkyl or aryl halide, magnesium metal and ether, must be absolutely dry. Ether used as a solvent must be completely free from alcohol. This can be done by first washing ether several times with water followed by drying over anhydrous CaCl2 for 1 to 2 days and subsequent distillation over sodium. An atmosphere of dry nitrogen should be maintained throughout the course of the reaction. These precautions are necessary since Grignard reagents are decomposed by moisture and react with the oxygen and carbon dioxide to form alcohol and carboxylic acid respectively. The ethereal solution of Grignard reagents thus obtained is generally used as such of various reactions by adding to it other reagents. Mechanism. The mechanism of the formation of the Grignard reagents is still not certain. According to the Gomberg and the Beckmann reactions commence with the formation of a small amount of magnesium halide and then proceeds by a free radical mechanism. This mechanism is also elegantly explain the initiating effect of iodine, which may be ascribed to the formation of magnesium iodide from magnesium and iodine. Structure of Grignard reagents. The structure of Grignard reagent has not been finally settled so far. The recent research has shown that the actual structure varies with the particular Grignard reagents and the solvent used for its preparation. Grignard and the Blazes observed that evaporation of ethereal solution of Grignard reagents resulted in a white solid having the compositions RMGX into 2C2H5 whole twice 2 O. They suggested that ether molecules were present as a ether of crystallization. X-ray analysis of these dietherates suggested that the four groups are arranged tetrahedrally as shown in Formula 1. The Formula 1 suggests that ether does not merely provide a medium of reactions for the reaction, but it also helps to dissolve the Grignard reagents formed due to the solvation by ether molecules. This is supported by the observation that Grignard reagents can be prepared even in benzene solution in the presence of tertiary amine, which coordinate with magnesium like ether and thus dissolves it. Further, Formula 1 shows the Grignard reagents in the monomeric form, but physical studies have revealed the Grignard reagents exist as a 1:1 complex of a dialkyl or diaryl magnesium and magnesium halide coordinated with the molecule of ether. These two species are held together by halogen bridge as shown in Formula 1. However, for the sake of convenience, the formula RMGX has been used to represent alkyl magnesium halides in the text. Reaction of Grignard reagents. The carbon magnesium bond in Grignard reagents is highly polar due to a large electronegativity difference between carbon and magnesium. Consequently, due to a greater electron density around carbon, the alkyl group in Grignard reagents can act as a carbanion anion or a nucleophile. That is, it attacks any electron deficient center in other molecules. In other words, Grignard reagents Kepler undergo nucleophilic substitution or nucleophilic addition reactions. Nucleophilic substitution reactions. Grignard reagents reacts with the compounds containing an active hydrogen or halogen atom. All such reactions involve the nucleophilic attack of alkyl group of the Grignard reagents on the electron deficient center as shown below. Nucleophilic addition reactions. Grignard reagents react with the compound having a multiple bond such as carbon oxygen bond, carbon sulfur bond, carbon nitrogen bond, sulfur oxygen, etc. to form addition products which when hydrolyzed yield a vast variety of compounds. In all such reactions, the addition of the nucleophilic group RMGX, that is R negative, occurs at the more electropositive and that of the MgX group at the more electronegative atom of the multiple bond. Thus, when carbonyl compounds and Grignard reagents react with each other, the addition product is formed and alcohol is formed by hydrolysis. Synthetic use of Grignard reagents. Grignard reagents serve as extremely valuable starting materials for the synthesis of vast variety of the organic compounds. They have attained an A position in synthetic organic chemistry unrivaled by any other classes of compounds. To illustrate this, some important synthetic application of the Grignard reagents are described below. Alkenes by action with the active hydrogen containing compounds such as water alcohol, thioalcohols, carboxylic acid, hydrogen sulfide, ammonia, amines, terminal alkynes, etc. reacts with the Grignard reagents to form an alkane corresponding to the alkyl or aryl group of Grignard reagents. When RMGX is react with the hydrogen and the RHMGX is formed, where B is the product OHOR, SR, etc. For example, this. When methyl magnesium iodide react with the water, methane is formed. Since methane is evolved quantitatively when CH3Mgi is treated with the compounds containing active hydrogen, therefore these reactions can be used for the estimation of alcohol, amine and SH group in the organic compounds. The method of employed is called gelatinous method. Aryl magnesium halide also behave in a similar manner. For example, when phenyl magnesium bromide is react with water, benzene magnesium hydrogen bromide is performed. By action with the reactive alkyl halide, Grignard reagents react with the reactive alkyl halides such as butyl chloride, benzyl chloride, etc. to form alkenes. When Grignard reagents react with the alkyl halide, alkane is formed. When methyl magnesium iodide is react with the tert butyl chloride, In the presence of dry ether, the new pentane is formed. When ethyl magnesium bromide is reacted with the benzyl chloride in the presence of dry ether, 1-phenyl propane is performed. Alkenes, Grignard reagents, being weak nucleophiles, do not react with the simple alkyl halides. However, compounds containing more reactive halogens, such as allyl, iodide, etc., react with the giving alkenes. For example, allyl iodide is performed to the product. Given product is 1-butane. Alkynes. Grignard reagents react with the terminal alkynes, forming alkenyl Grignard reagents, which upon treatment with the alkyl halides give higher alkynes. For examples, propyne react with RMGX is propyl magnesium iodide is formed. Primary alcohol by action with the ethylene oxide followed by hydrolysis. Grignard reagents react with the ethylene oxide to form addition product which on hydrolysis with dilute hydrochloric acid for primary alcohol containing 2 carbon atoms more than the alkyl halide. When ethylene oxide is react with the Grignard reagents, the addition product is formed and by hydrolysis primary alcohol is performed. For example, ethyl magnesium bromide react with the react with this addition product is formed. By action with formaldehyde followed by the acid hydrolysis, when treated with the formaldehyde, Grignard reagents form an adduct with which on the hydrolysis with dilute hydrochloric acid gives a primary alcohol. Formaldehyde is reacted with Grignard reagents, then addition product is formed and by hydrolysis primary alcohol is performed. By action with oxygen, primary alcohols are performed by passing dry oxygen through the solution of Grignard reagents followed by acid hydrolysis of the resulting addition product. Secondary alcohol by action with aldehyde or other than formaldehyde followed by the acid hydrolysis acetaldehyde in the presence of Grignard reagents hydrolyzed by secondary alcohol is formed. By treating an excess of Grignard reagents with ethyl formate, the reaction takes place in 2 steps. Grignard reagents first reacts with the ethyl formate to form a aldehyde, which in turn reacts with the another molecule of Grignard reagents to yield an adduct, which forms a secondary alcohol on hydrolysis. When ethyl formate is reacted with Grignard reagents, then addition product is performed and the aldehyde is performed. Tertiary alcohol by action with ketone followed by the hydrolysis. When ketone is reacted with Grignard reagents, then tertiary alcohol is performed. Then acetone is reacted with Grignard reagents. Then 2-methyl 2-butanol is product present as a product. Acetophenones is reacted with Grignard reagents. Then by hydrolysis, given product is 1,1-diphenylethanol. A tertiary alcohol having at least 2 similar alkyl group may be prepared by the interaction between an ester other than formic acid ester and an excess of Grignard reagents. The reaction proceeds in 2 steps. Ester is reacted with Grignard reagents, then addition product is performed and the ketone product is performed. By reaction with the acid chloride and anhydride, Grignard reagents react with the acid chloride or an anhydrides to give addition product which upon an acid hydrolysis given tertiary alcohol, the reaction takes place in two stages. When acid chloride is react with the Grignard reagent, then addition product is performed, and when react with the magnesium chloride, then perform the ester. For example, acetyl chloride is react with the Grignard reagents, then perform the acetone, and by hydrolysis given product is tert-butyl alcohol. Ethers. Grignard reagents react with the lower halogenated ether to yield higher ethers. Monochloromethyl ether is react with the Grignard reagents, then ethyl methyl ether is product given product. Aldehyde. When a Grignard reagent is treated with the ethyl formulate, an aldehyde is formed. However, with the excess of Grignard reagents, the product obtained is a secondary alcohol. For example, ethyl formate is react with RMGX, then aldehyde is formed. For example, ethyl formate is react with the ethyl magnesium bromide, then by hydrolysis the propenyl aldehyde is formed. Aldehyde are obtained in a bitter yield if ethyl orthoformate is employed instead of ethyl formate. This is so since the formation of acetyl in this case prevents the formation of secondary alcohol. When ethyl orthoformate is react with the Grignard reagents, then acetyl is formed, and by hydrolysis aldehyde is formed. Aldehyde may also be obtained by the interaction between Grignard reagents and hydrogen cyanide, followed by the hydrolysis of the adduct formed. When hydrogen cyanide is react with Grignard reagents, then the addition product is formed, and by hydrolysis the aldehyde is formed. Ketones. By treatment with the alkyl cyanide followed by the acid hydrolysis, for example, acetonitrile reacts with the uh, Grignard reagents, then by hydrolysis ethyl methyl ketone is formed. By action with the acid chlorides, as discussed on 83 page, equimolar amounts of the Grignard reagents and an acid chloride have an addition product which forms ketones on hydrolysis. If Grignard reagents is used in excess, tertiary alcohol are obtained as ultimate products of the reactions. When acid chloride is react with Grignard reagents, then ketone is formed, and by hydrolysis is tertiary alcohol is formed. Monocarboxylic acids, Grignard reagents, interact with dry ice to form addition products with which of acid hydrolysis give monocarboxylic acids. When Grignard reagents is react with the carbon dioxide, then addition product is formed. By hydrolysis, monocarboxylic acid is the formed. Ether. By action with ethyl chloroformate, equimolar amounts of Grignard reagents and ethyl chloroformate reacts together to form higher ester. Ethyl chloroformate when react with Grignard reagents, then addition product is formed, and then higher ester is formed. For example, ethyl chloroformate is reacts with the Grignard reagents, then ethyl acetate is formed by in the presence of magnesium chloride. Thioalcohols, Grignard reagents react with the sulfur to give an addition product with which gives a thioalcohol on hydrolysis. Phenol. Aryl magnesium halide reacts with the oxygen to form addition product with which the upon the hydrolysis give phenols. Phenyl magnesium bromide reacts with uh, O2 half mole of O2 dry ether. In the presence of dry ether, phenoxy magnesium bromide is formed as a product, and by hydrolysis is phenol is formed. Al- Alkyl cyanide by interaction of Grignard reagents and cyanogen cyanogen chloride or cyanogen RMgX reacts with the cyanogen chloride, then alkyl cyanide is formed. Excess of Grignard reagents is avoided since it will react further with alkyl cyanide to yield ketones. Primary amines. Grignard reagents react with the chloramine to form primary amines. When ethyl magnesium bromide react with the ammonium chloride, then ethylamine is formed as a product. Reasonable yield of primary amines is obtained only with the Grignard reagents containing tert alkyl group. Primary amines can be prepared is satisfactory yields by action of a Grignard reagents on orthomethyl hydroxylamine. When alkyl magnesium chloride is reacted with orthomethoxy metho- methyl dioxylamine reacts with them, primary amine is formed by hydrolysis of product. Sulfonic acid. On passing sulfur dioxide into a well-cooled solution of a Grignard reagent, in addition product is obtained with which of hydrolysis gives sulfonic acid. When sulfur dioxide is reacted with Grignard reagents, then addition product is formed, and by hydrolysis sulfonic acid is formed as a product. Dithionic acid. These are prepared by the action of Grignard reagents with which carbon disulfide followed by acid hydrolysis. When carbon disulfide is reacts with Grignard reagents, then addition product is formed, and by hydrolysis dithionic acid is formed. Organometallic compounds, Grignard reagents and inorganic halides interact with each other, resulting in the formation of other organometallic compounds. Abnormal addition of Grignard reagents, addition of hindrand ketones. If the Grignard reagents or the ketone contains branching at the alpha carbon, sometimes the usual addition reaction does not occur due to the steric hindrance. Instead, reduction occurs in which a hydride ion is transferred from the Grignard reagents to the ketone via the six-membered cyclic transition state in a manner similar to the Mirvan-Pondorf-Valery reduction. For example, when isopropyl magnesium bromide is added to dipropyl ketone, the expected tertiary alcohol is not formed. Instead of the secondary alcohol, diisopropyl carbonyl is obtained by the reduction of the keto group. When isopropyl magnesium bromide is reacted with diisopropyl ketone, then propane is formed, and by hydrolysis the diisopropyl carbonyl is formed as a product. Addition of alpha beta unsaturated compounds. Alpha beta unsaturated carbonyl compounds react with the Grignard reagents to give a 1,2 and 1,4 addition products. The orientation of addition is often controlled by steric factor. In general, substitution at the carbonyl group favors 1,4 addition, while substitution at a double bond favors 1,2 addition. For example, 1,2,3 triphenylpropane 2 prop 2 ene 1 1 on. Then by hydrolysis the 1,4 addition product is formed. In the most cases, both products are formed, but alpha-beta unsaturated aldehyde nearly always gives exclusively 1,2 addition product. When treated with Grignard reagents, however, then the extent of 1,4 addition of Grignard reagents can be increased by the carrying out the reaction in the presence of cuprous chloride and the cupric acetate, etc. This is called conjunction addition, and the probably occurs by the free radical mechanism. Limitation of the Grignard synthesis. Grignard reagents suffer from the following limitations. Grignard reagents are sensitive to moisture, oxygen, and the carbon dioxide, and hence must be protected from them. This makes the handling of Grignard reagents difficult. Grignard reagents cannot be prepared from alkyl halide containing other reactive functional groups such as OHSH, NH2 and COOH, SO2, CHO, aldehyde, ketone, ester, ketonic group and cyanide group. Since they all are reacted with them, only alkyl halide containing a few other groups such as R group, OR group, AR, and aromatic groups and the halide group can be used to form the Grignard reagents. Generally, branching of the carbon chain near the functional group prevents reaction probably due to the steric hindrance. For example, CH3-MgBr and or CH3-MgI does not react with the dietert-butyl ketone. That is, similarly, if the Grignard reagents containing the large alkyl group, the reaction is the sometimes prevented again due to the steric hindrance. For example, the isopropyl methyl ketones react with the CH3-MgI but not with the tert-butyl magnesium chloride. Compounds which are the capable the enolizations liberate hydrogen with the Grignard reagents. For example, when ethyl acetoacetate is reacts, then the enol formed and the reacts with the CH3-MgI, then enol forms. Nitro compounds cannot be used in the Grignard synthesis since they oxidize the Grignard reagents. Despite the above limitations, Grignard reagents are still the most important tools in organic synthesis. Organogen compounds. Although organogen compounds of the types of R2Zn are not commonly used in the organic synthesis, they are particularly useful when the milder reagents are required. Methods of formation. Following methods have been used to preparation of organogen compounds. From alkyl halides. Alkyl iodides reacts with the zinc copper couple in higher boiling ether to form alkyl zinc iodides, which upon the subsequent distillation in the atmosphere of CO2 undergo disproportions reactions to give dialkyl zinc compounds. Distillation by distillation process. 4. Organo-aluminum compounds. Treatment of trialkyl aluminum with zinc chloride give dialkyl zinc compounds. When ZnCl2 reacts with the triethyl aluminum, then diethyl zinc compounds is formed. This method forms the basis of laboratory preparation of these compounds. Physical properties. Then dialkyl zinc compounds have linear geometry due to the sp hybridization zinc compounds atoms. They are non-polar, non-polar boiling liquids or low melting solids soluble in organic solvents. The lower zinc compounds are highly inflammable in air and hence are usually prepared and used under CO2 atmosphere. Chemical reactions. The chemical reactions of organogen compounds are similar to those the Grignard reagents with the only difference that they are less reactive. For example, they do not react with CO2 and react only slowly with cyanide, ketones, and esters. Some of important chemicals reactions of dialkyl zinc compounds are discussed below. Reaction with water. They are readily react with water forming alkenes. Reactions with alkyl halides. Dialkyl zinc compounds do not react with primary, secondary alkyl halides. They react with only with tertiary alkyl halides to form alkenes containing a quaternary carbon atom. When tert-butyl chloride is reacted with dimethyl zinc, then new pentane is formed. Reaction with the acid chloride. They react readily with the acid chlorides to form ketones. For example, diethyl zinc is reacts with acetyl chlorides. Then butane is formed. Ketones are obtained in good yields because dialkyl zinc compounds react very slowly with them. Reformatsky reactions when an aldehyde or a ketone is added to the solution of an alpha haloester in the presence of zinc, an organozinc compound is the first formed with the beta hydroxy ester. This reaction is called reformatsky reactions and is useful method to preparing beta hydroxyester acids and their derivatives. For example, ethyl bromoacetate reacts with zinc in the presence of dry ether, then organozinc compounds is formed. And when acetaldehyde reacts with zinc compounds and the addition product is formed, and by hydrolysis the ethyl beta hydroxybutyrate is formed. Similarly, the benzaldehyde reacts with ethyl bromoacetate in the presence of zinc, and by hydrolysis the ethyl beta hydroxy beta phenyl propionate is formed. Iodo iodomethyl zinc iodide. Iodomethyl zinc iodide is an important organozinc compound and is obtained by the action of zinc and copper coupled on the methylene iodide. In the presence of diethyl ether, the iodomethyl zinc iodide is formed. It reacts with the olefins to form cyclopropane derivatives. When olefin is react with zinc compound, the cyclopropane derivatives is formed. This reaction is called Siemens-Smith reactions and is used to preparation of cyclopropane derivatives. The addition occurs in the stereospecific synthesis manner according to the following consort mechanism. Cis-2-butane reacts with zinc compounds, then transition state is formed. Cis-1,2-dimethyl cyclopropane is formed as a product. Organolithium compounds, compound in which lithium atom is directly bonded to the carbon atom are called organolithium compounds. For example, methyllithium, ethylithium, N-butyllithium, phenyllithium. Organolithium compounds are more reactive than Grignard reagents and also undergo a few additional useful reactions. Therefore, they are widely used in organic synthesis these days. Formation of alkyl lithiums. By the reaction of alkyl halides with lithium, alkyl lithiums are generally prepared by treating an alkyl halide with lithium in hexane, benzene, or any other hydrocarbon solvent at a low temperature in an inert atmosphere of nitrogen or argon. When alkyl halide is reacted with lithium in the presence of dry hexane, then, then alkyl lithium is formed as a product. For the preparation of alkyl lithiums, hydrocarbon solvents are preferred over ether since the uses of ether not only encourage Wood reaction but also with it. Diethyl ether reacts with N-butyl lithium, then butane is formed as a product and the ethylene is formed as a product. By metal-metal exchange, alkyl lithium can be readily prepared by the replacement of one metal by another. For example, diethyl mercury reacts with lithium in the presence of ligurian at temperature 338 Kelvin temperature, then ethyl lithium is formed as a product. Chemical reactions with alkyl lithiums. The carbon lithium bond is more polar than carbon magnesium bond. Therefore, alkyl lithium are more reactive than the Grignard reagents except a few differences. Their chemical behavior is similar to that of the Grignard reagents. Some of their important chemical reactions are discussed below. Resemble with the Grignard reagents. They resemble Grignard reagents in the most of their reaction of some of these reactions are formation of hydrocarbons like Grignard reagents. They react with the compounds containing active hydrogen to form the corresponding hydrocarbon. For example, when methyl lithium is reacts with the water, then methane is formed. as a product. Formation of primary, secondary, and tertiary alcohol. Primary alcohol by action with formaldehyde. When formaldehyde is reacts with alkyl lithium in the presence of hexane, the addition product is formed. Then, by hydrolysis, primary alcohol is formed. For example, this like Grignard reagents, alkyl lithium compounds also reacts with the ethylene oxide to form primary alcohols containing two carbon atoms more than the starting alkyl or aryl group. When phenyl lithium is reacts with ethylene oxides in the presence of hexane and the by hydrolysis 2-phenyl ethanol is formed as a product. Secondary alcohol by action with the aldehydes other than formaldehyde. Then acetaldehyde reacts with the lithium compounds. Then in the presence of hexane, then the by hydrolysis isopropyl alcohol is formed. Tertiary alcohol by action with ketones. When acetone is reacts with the alkyl lithium in the presence of hexane, then by hydrolysis tert-butyl alcohol is formed as a product. Formation of ether by action with monochloroether. Monochloroether is reacts with alkyl lithium in the presence of hexane. Then ethyl methyl ether is formed as a product. Formation of aldehyde by action with the ethyl orthoformate or hydrogen cyanide. Hydrogen cyanide reacts with the alkyl lithium in the presence of hexane. Then by hydrolysis acetaldehyde is formed as a product. Then ethyl chloroformate is reacts with lithium compounds in the presence of hexane. Then by hydrolysis acetaldehyde is formed as a product. Formation of ketones by action with any orthoester other than orthoformic ester or alkyl cyanide. For example, ethyl orthoacetate reacts with lithium compounds then in the presence of hexane. Then by hydrolysis acetone is formed as a product. Acetonitrile reacts with ethyl lithium in the presence of hexane. Then by hydrolysis butanone is formed as a product. Formation of nitriles by action with cyanogen chloride. Then cyanogen chlorides react with lithium compounds in the presence of hexane. The acetonitrile is formed as a product. Reaction with alkyl halides. Alkyl lithium reacts with alkyl halides to form alkanes. For example, ethyl lithium reacts with CH3Br Grignard reagents in the presence of hexane. Then propane is formed. Reaction with aryl halides. Aryl halides undergoes nucleophilic substitution reactions by elimination, addition, or benzene mechanism. For example, when orthofluoroocyanol colinsanol is reacts with elimination reactions in the lithium compounds, benzene is formed as a addition product is mm, formed 3-phenyl anisole. Tertiary phenyl anisole is formed as a product. Reaction with the heterocyclic compounds. Heterocyclic compounds undergoes nucleophilic substitution reactions by bimolecular displacement mechanism. For example, pyridine reacts with pyridine reacts in the presence of aromatic substitution aromatic lithium compounds at temperature 383 Kelvin temperature. Then 2-phenylpyridine is formed as a product. The difference from the Grignard reagents. Organolithium compounds being more reactive than Grignard reagents undergo some additional reactions as discussed below. Action with carbon dioxide. Grignard reagents yield carboxylic acid with carbon dioxide while organolithium compounds yield ketones. When carbon dioxide reacts with alkyl lithium in the presence of hexane, then unstable state is formed in intermediate, and by hydrolysis ketone is formed as a product. This difference is due to the reason that organolithium compounds are more strongly nucleophilic than Grignard reagents and thus reacts further with the intermediate resonance stabilized carboxylate anion giving ketones. Action with carboxylic acid, alkyl lithium compounds reacts with carboxylic acid yielding ketones as the main product. Grignard reagents, on the other hand, give alkanes corresponding to the alkyl group of the Grignard reagents. Benzoic acid reacts in the presence of alkyl lithium and hexane. Then, by hydrolysis, acetophenone is formed as a product. Addition to the carbon-carbon double bond. Unlike Grignard reagents, organolithium compounds add to the simple alkenes to give a mixture of compounds. The addition occurs at high pressure, 100 to 500 atmosphere. For example, when alkyl lithium reacts with alkene in the presence of hexane, then the products are formed. Formation of tertiary alcohol. Organolithium compounds being more nucleophilic and smaller in the size, the corresponding Grignard reagents add to strictly hindrant ketones to form strictly hindrant tertiary alcohol. Grignard reagents, on the other hand, do not give such addition reactions. For example, isopropyl lithium adds to diisopropyl ketones to yield triisopropyl carbonyl. When, isopro- when isopropyl lithium reacts with diisopropyl ketones in the presence of hexane, dihexane, then triisopropyl carbonyl is formed as a product. In contrast, when isopropyl magnesium bromide is added to the diisopropyl ketone, then expected tertiary alcohol is not formed. Instead, reduction of the ketone by the Grignard reagents occurs to give diisopropyl carbonyl and the propylene. Then reaction with the alpha beta unsaturated carbonyl compounds. Organolithium compounds, being more nucleophilic, predominantly undergoes the 1,2 addition to alpha beta unsaturated carbonyl compounds, whereas Grignard reagents give mainly 1,4 addition product. For example, benzolenic and at the presence of hexane, 1,2 addition product is formed. Thank you guys.